This is project test 5, video number 3, and this will be problems 22 to 30. And if you're wondering where 21 is, item 21 was not scored. So that should make you feel better to know that even College Board, with all the millions of dollars they take in from you guys, they still make errors in writing their own tests. It makes me feel better because I make errors as well. Okay, so number 22. As I said, 21, they did not score, so we don't even have the question. The faces of a four-sided die are numbered 1 through 4, respectively, for a certain game. The die is tossed and the number that lands down is recorded. The table below summarizes the points a player earns for the number that lands face down. So apparently you get 0 points if it lands on a 1, 1 point if it lands on a 2, 0 points if it lands on a 3, or 2 points if it lands on a 4. Consider 2 independent tosses, and that's should be a scary phrase to us. As soon as we see that, we know we need to make some sort of space. So I'm going to go ahead and make a sample space of what could happen. By the way, this is going to be a fairly long problem, so this is going to take a little bit of time to do. So I can get on the first roll, I can get a 1, 0, 1, 1. Excuse me, I'm doing that all wrong. I can get a 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Well, that's all the different combinations I can get. But that doesn't line up to what they have because we have different point values. Now, I'm going to tell you that when I have a problem like this, I sort of cheat. I sit there and go, you know what? We're going to make this as simple as possible. But first off, I need to do some replacements. If I get a 1, 1, I get a 0 for the 0 points and 0 points. So this is going to be, when I actually start replacing points in, I'm going to have to match. Every time I have a 1, I get a 0. Every time I have a 2, I put a 1, etc. All right. So this is going to be 0, 0, 0, 1, 0, 0, then 0, 2, 1, 0, 1, 1, 1, 0, 1, 2, 0, 0, 0, 1, 0, 0, 0, 2, and then I'm going to have a 2, 0, 2, 1, 2, 0, 2, 2. I'm going to go ahead and move this so we can see a little better. So that's what I ended up with. Okay. Now, and all I did was every time I had a 1, I put a 0 in. Every time I had a 2, I put a 1 in. If I had a 4, it got a 2. And if I had a 3, it got a 0. So that's how I ended up with that table. Well, if I sum these together, this becomes 0. This is 1, 0, etc. I'm like, oh, that's where they get the distribution from. I could have 0 and 0 gives me 0. 1 and 0 gives me 1. 2 and 0 gives me 2. I could have 2 and 1, and that gives me a 3. And I have a 2 and a 2, and that sums to give me 4. So I'm going to look at my answer choices, and I need to make sure I'm able to get a 0, 1, 2, 3, or 4. And it turns out the only ones I can get a 0, 1, 2, 3, or 4 are D and E. All right, so that gets rid of A, B, and C. So A, B, and C are gone. Now it's like, well, the only way I can get a 4 is a 2 out of 2. So let's check that out. I have 1, 2, 3, 4, 16 possibilities, and 1 over 16. What does that equal? 1 divided by 16. 0.0625. That does match up, so I feel pretty good about that. Then I want to sit there and go, you know what? What's going to be easiest? And I look to see where they differ. And I'm like, hey, they differ at 0. So I know it's going to be one of these two, so let's see which one matches. Well, that sums to 0. This sums to 0, this sums to 0, and this sums to 0. Those are the only U's that sum to 0, and that's 4 out of 16, which is 0.25. This is 0.25. This is wrong. My answer to number 22 is D. Time-consuming problem, but if you take a moment to do all the sample space work, it's a very doable problem. Just have to take that moment to do all the sample space work. Number 23. A botanist collected one leaf at random from 10 randomly selected mature maple trees of the same species. The mean and the standard deviation of the surface area of the 10 leaves in the sample were computed. Assume the distribution of surface areas of the maple leaves is normal. What is the appropriate method for constructing a one sample confidence interval to estimate the population mean surface area of the species? All right, and why is the method appropriate? The mean and the standard deviation, let's look at this. The mean and the standard deviation in the sample were computed. So we're using the standard deviation of the sample. Standard deviation of the population, and we're working with the mean, that's a Z. Standard deviation of the sample, and we're working with the mean, that's a T. Regardless whether you're talking about an X bar, these follow that way. So T interval is appropriate because the population standard deviation is not known. And we know it's not known because we use the sample. All right, so the answer to 23 is A. Number 24. A state education agency was concerned that the salaries of public school teachers in one region of the state, Region A, were higher than that in Region B. So they think Region A is greater than Region B. The agency took 2 independent random samples, yay, of salaries of public school teachers, one from A and one from B. The data were summarized in the table. Assuming all conditions for inference are met, do the data provide convincing statistical evidence that the salaries of public school teachers in A are on average greater than that in B? Now, please remember, our null hypothesis is going to look like this. Mu A equals mu B, and HA mu A is greater than the mean of B. All right, so they didn't give us a p-value, so we're going to have to go ahead and run this test, stat test, and we have 2 samples. We're working with means, which makes it a t. Well, we're using the standard deviation of the sample, which makes this a 2-sample t. So 2-sample t-test. And we have 62,583 is our sample mean. 6,274 is our standard deviation. Sample size 117. Standard deviation of 60,117. 9,319. Sample size is 78. And our alternative hypothesis is a greater than. And I end up getting a p-value of 0.02. All right, so my p-value is 0.021. All right, so p-value 0.021, I compare it to 0.001, it's greater than 0.001, so not enough evidence. I compare 0.0213 to 0.01, it's greater, not enough evidence. I compare 0.0213 and it's less than 0.05, so there is enough evidence at 0.05, but it's greater than 0.01, so yes at 0.05, but not at 0.01. 24 is C. In other words, we're saying 0.01 is less than 0.02 is less than 0.05. So we're significant here because we're less than, but we're greater than here. All right. So that's what all we're doing is we're just sitting there going, where does our p-value fall? So it's significant at 0.05, but not at alpha of 0.01. A florist wanted to investigate whether a new powder added to the water of cut flowers helped to keep the flowers fresh longer than just water alone. For a shipment of roses that was delivered to the store, the florist flipped a coin before placing each rose in its own individual container with water. If the coin landed heads up, the rose was placed in water with new powder. Otherwise, the rose was placed in water alone. So basically, here's what we have. Random assignment, water, water with powder. Which of the following is the best description of method used by this florist? First off, we have an experiment. Why? We have random assignment of treatments. We randomly assigned it either to water or water with the powder. And we don't have any blocking, et cetera. So this is a completely randomized design. All right. A commercial for a breakfast cereal is shown during a certain television program. The manufacturer of the cereal wants to estimate the percent of television viewers who watch the program. The manufacturer wants the estimate to have a margin of error of at most 0.02 at a level of 95% significance. Of the following, which is the smallest sample size that will satisfy the manufacturer's requirements? So first off, here's my confidence interval formula. And this right here equals the margin of error. And they want the margin of error to be no more than 0.02. All right, so we know we're looking for n, so I'll go ahead and draw that in there. And we need to calculate our z star. So second vars, inverse norm, parenthesis 1 minus 0.95, close parenthesis, divided by 2. Mean is 0, standard deviation of 1 because we're working with a z. And we get about 1.96. Because we have no estimate for p hat, we don't have an estimate for p hat, we have to use the largest value possible, which is going to be 0.5. So when there is no estimate, that's what you use. I'm going to divide both sides by 1.96. And I'm going to multiply these and get 0.25. So I have 2.25 over n equals 0.02 over 1.96. I'm going to square both things. This gives me 0.25 over n equals 0.02 over 1.96 squared. So 0.02 divided by 1.96. I'm going to go ahead and square that. And I'm going to take 0.25 and divide it by that value that we just calculated. And I end up getting 2,400. And it always rounds up to 1. So 2,000, we always round it up. So 2,401. So I want the smallest number that is larger than 2,401. That answer is E. So my answer choice for this number is E. And I know, and by the way, if they would have had 2,400 as an answer choice, I would have drawn a line from it through it and still selected this one because it has to be at least 2,401. 2,400 was not big enough, so I would have had to go to 2,401, which would push me to, even if they'd had 2,400, I still would have had to chosen 2,500. All right, 27. A contestant's final winnings on a game show are determined by a random selection of the base amount and possible multiplier. For the base amount, the contestant randomly selects one of 4 cards where 2 are marked 1,000. So we can get $1,000, and the probability of getting that is 2 out of 4. One card is marked $2,000, so we have a $2,000 card, and there's a 1 in 4 chance of getting that one. And there's another card marked $5,000, and there's a 1 in 4 chance of getting this one. After choosing the card, the contestant randomly selects one of 5 chips. Okay, so we got 5 chips, where 3 chips are red and 2 are white. So 3 out of 5 are red, 2 out of 5 are white. If the selected chip is red, the contestant's final winnings are double. So if they're red, it's times 2. If they're white, it's just times 1. They don't change. All right. What is the probability that a contestant's winnings are exactly 5,000? Well, nothing here that I multiply are exactly 2,000. Nothing I multiply here will give me the work with the 5,000, so that's gone. But if I draw a red chip, it doubles, and this would be times 2. If I draw a white chip, this is times 1, that stays 2,000, and the probability of doing that is 2/5. Well, this becomes 6 over 20. This becomes 2 over 20. That equals 8 over 20, which is 0.40. All right. And all I did, 2/4 times 3/5. The probability of getting a 1,000 times the probability of getting a red. Probability of getting 2,000 times the probability of getting a white. And that will equal 40%. And my answer is E. Number 28. Meteorologists are interested in the relationship between minimum pressure and maximum wind speed of hurricanes. The minimum pressure in millibars and the maximum wind speed in knots were collected for a random sample of 100 hurricanes from the year 1995 to the year 2012. A regression analysis of maximum wind speed on minimum pressure. And by the way, this is a weird way of expressing this. So we have wind over pressure, all right? Produce a 95% confidence interval of negative 1.42 to negative 1.2 for the slope of the regression line. Which statement is a correct interpretation? So wind decreases for pressure increase. And usually this is going to be 1. So we're saying, all right, and the reason I know it's decreasing because this is negative. So it's negative 1.42 over 1 to negative 1.2 over 1. Essentially, we're saying this is what our slope is. We're 95% confident that our slope is negative 1.42 over 1 to negative 1.2 over 1. So for every 1 pressure increase, we have somewhere between a negative 1.4 and negative 1.2 decrease in wind speed. The probability is 0.95 that the wind speed will decrease And we really don't like the word probability, okay? I know that showed up one time, but that's really a bad answer. So we really don't like probability. The probability is 0.95 at a different sample, and we don't like, I don't know, where they came up with this idea of a different sample. And they also said probability again. We can be 95% confident that wind speed decreases on average between 1.2 and 1.42 knots for every one increase in pressure. And sure enough, we have a positive 1 in the denominator, and we're decreasing negative 1.42 to negative 1.2. C is our best answer. All right, and the problem with this is it says increase. And this says for any sample. All right, and no, we're not sure for any sample because there's a 5% chance that our sample is wrong. So we can't say that for any sample. Our sample could be wrong, in which case none of it applies. But we are confident that the slope of the regression line is between here, which means it's going to decrease between 1.2 and 1.42 knots for every 1 millibar increase. Number 29. Some contact lens wearers report problems with dryness in their eyes. A study was conducted to evaluate the effectiveness of a new eye drop solution to relieve dryness for contact lens wearers. 25 volunteers who wore contact lenses agreed to the new solution for 1 month. At the end of the month, 36% of the volunteers reported the new solution was effective in relieving dryness. The company that produced the new eye drop concluded that using the new solution is more effective in relieving dryness than no solution. Which of the following best explains why the study does not support the conclusion? Well, the sample size probably is too small, so that's probably a good choice. The study had no control group. Wait a second. That's right. There's nothing to compare this to. We're saying it's more effective than relieving dryness than no solution. There was no group that had no solution. No solution, because I have to be a valid experiment, I need 2 treatments. In this case, I only had 1 treatment, so I had no control group. This was not an experiment. I cannot make that claim. Okay, so that is a better choice than the fact that it was too small. It was wrong from the get-go. The management team of a company with 10,000 employees is considering installing charging stations for electric cars in the company parking lots. In a random sample of 500 employees, 15 reported owning an electric car. What is the 99% confidence interval for the proportion of all employees at the company who own an electric car? So remember our confidence interval, P hat plus or minus Z star, P hat, Q hat over N. So P hat is going to be 15 over 500, which is 0.03. So 0.03 plus or minus, we'll come back to Z star in a moment. 0.03 times 0.97, that's the 1 minus the 0.3 over the sample size of 500. And now we need to go back and calculate Z star. So second vars, inverse norm, parenthesis, 1 minus 0.99, close parenthesis, divided by 2. 2.576. So 0.03, 2.576. That's it. So the answer for number 30 is C.